In this video, we'll discuss and contrast two different types of learning, discriminative and generative learning. So we'll say that a learning algorithm corresponds to a discriminative learning algorithm if it's trying to optimize a conditional likelihood. That is, if it's trying to optimize a loss function, which looks at minus the log of the probability of the true target given x. So for instance, conditional random fields are usually trained in a conditional way. And they actually always train conditionally because a conditional random field only defines a conditional distribution. It actually doesn't really look at defining a distribution just over x, or a joint distribution over y and x. Another alternative actually would be to do generative learning. That is, to optimize the joint log likelihood. So in other words, optimize minus the log of the joint probability of observing y and x, as opposed to the probability of observing y given that I'm observing x. So for instance, HMMs are usually trained generatively. So if you know about HMMs, what you've probably seen is the learning algorithm for training them generatively. Though we could also train it in this way, because if I give you a joint distribution over y and x, I can then do the inference of what is p of y given x, and then I could try to train it discriminatively. But initially, HMMs have mostly been developed and proposed in the context of generative training. And so let's exploit that formula a little bit. So we have that the joint distribution is can be written down as the product of the conditional p of y given x times the marginal p of x. And because the log of a sum is the sum of logs, then this is also equal to minus the log of p of y given x minus the log of p of x. So we see that the difference is this term here. So we have this here and this here, but we have this term that is added when we're performing generative learning. And so one way of thinking about this is that perhaps this term is kind of acting like a regularizer. That is, we're adding another term which does not involve y. So it's not a term that encourages the model to assign high probability to the true target given x. It's just a model that requires to do something else. It's going to favor models that also explain well the marginal, so assign high probability to observing true data, so the data, just the inputs that we see from the training set. And so for that reason, a good intuition is to think that discriminative learning will tend to fit the data better, while generative learning will be more regularized because of this term here. Actually, we can show that there are two scenarios that we can observe in terms of how generative versus discriminative learning will comparatively compare. So if a model is well specified, so that means that the data in our training set was actually generated from a model from the same class as our model. So there's a setting of our parameters for our model that corresponds exactly to the true model that generated the data. So if the model is well specified, then we can show that generative learning is essentially always better. That is, for any size of training set that we use, there's always going to be a gap between what generative learning gets in terms of generalization performance compared to discriminative training. So generative training is going to perform better. They should both eventually converge to essentially an error zero, so a perfect performance. But generative learning is going to get there much faster. However, if the model is not well specified, which is really most of the time, so if data was generated by some experts that labeled some data, then this is a process that is almost certainly more complicated than the model we've written down in math. So really, this is essentially for all interesting problem, the model will tend to be will not be well specified. then the picture is not as clear. So what we'll see is a picture that is consistent with the view that generative learning is just more corresponds to more regularization. So if the training set is small, then we should observe that generative learning will get a better performance in terms of generalization. But as we increase the size of our training set, eventually we should reach a point where discriminative learning will catch up with generative learning and will start being actually better in terms of generalization performance, so get lower generalization error than generative learning. And in fact, more specifically, what we get is that discriminative learning will converge to a smaller asymptotic error, asymptotic error being the error your model would get if you had infinite amount of training data. So it has a smaller asymptotic error than generative learning, which won't be able to do as well even with an infinite amount of training data. Okay, so again here, a nice way of, so a simpler way of interpreting this is that generative learning means more regularization. So if there's a small amount of training data, generative learning will probably do better. But if I have quite a bit of training data, then now we can expect discriminative learning to eventually catch up and do better. So that's actually a good thing to know about if you're tackling a problem for which you either have a lot of data or not a lot of data, so you know which kind of learning you should prefer. And for more theoretical details on this, I invite you to consult this paper on discriminative versus generative classifiers. So this is a paper by Andrew Ng and Michael Jordan, 2001.